Why are quantum cryogenic systems so big and energy hungry? Have you ever wondered why quantum cryogenic systems take up so much space and use so much energy? Let's break it down in a way that's easy to understand. Quantum computing relies on qubits, which are the building blocks of quantum information. To keep these qubits functioning properly, they need to be kept at extremely low temperatures, close to absolute zero, around 0.15 Kelvin. This is essential to maintain their quantum coherence, which allows for reliable computations. To achieve these frigid temperatures, we use complex cooling systems known as dilution refrigerators. These refrigerators requiring liquid helium and multiple cooling stages to reach the necessary temperatures. The energy needed for this cooling process can be quite substantial, often ranging from 25 to 50 kilowatts for each quantum computing unit. This makes the cryogenic system the largest energy consumer in the entire quantum computer setup. The size of these systems is not just about the cooling. It also involves multiple layers of thermal shielding and vacuum insulation. These components help isolate the qubits from any environmental heat or electromagnetic noise. Even the tiniest thermal fluctuations can disrupt the delicate quantum states, leading to errors in computations. As a result, the cryogenic apparatus includes bulky hardware like compressors, pumps, and heat exchangers, which all contribute to the overall size. When we look at energy consumption, the cooling system accounts for about 70% of the total power usage of a quantum computer. The remaining energy is used by control electronics that manipulate and read out the qubits, along with auxiliary systems like vacuum pumps and environmental controls. To put this in perspective, the annual energy use of a single quantum computer can be comparable to that of dozens of average households. Different quantum computing architectures have their own cooling requirements. For instance, superconducting qubits need those ultra-low temperatures, which is why they requiring large cryogenic systems. On the other hand, technologies like neutral atom quantum computers operate at higher temperatures and generally consume less energy. However, superconducting qubits are currently the most common due to their performance advantages. Researchers are actively working on ways to reduce the size and energy demands of cryogenic systems. This includes developing more efficient refrigerators and exploring qubit technologies that can operate at higher temperatures. Integrating cryogenic-compatible classical electronics is another approach to minimize heat loads. These advancements are essential for scaling quantum computers to accommodate more qubits while managing energy consumption and physical space. In summary, quantum cryogenic systems are large and energy hungry because maintaining the extreme cold temperatures necessary for superconducting qubits requires complex refrigeration hardware. This hardware is designed to protect fragile quantum states from environmental disturbances, presenting a significant challenge in quantum computer architecture that researchers are continuously addressing.